Hello everyone, my name is Yatin Gupta and I welcome you all to my channel Double E Concepts. So in the series of basics of network theory, this is the third part in which I'm going to talk about capacitors, which is the third circuit element that we're going to cover today, and in which I'll first talk about some general equations related to capacitor, and then we'll also see that how a capacitor behaves whenever it is connected across a DC source. So the format of this lecture is going to be similar that we saw in the previous one, which was related to inductors. All right, so let's begin today's lecture. So if we go by the definition, then it says that if the voltage across an element is proportional to the integral of current with respect to time, then that element is called capacitor. I have already told you that if you want to know that what kind of element it is, you always try to see the IV characteristic of that element. So in case of capacitor, the VC here will be proportional to the integration of this current with respect to time, and the capacitor is designed to store the energy in the form of electric field. I have already told you that capacitor and inductor both store and deliver the energy, they never dissipate the energy. The only difference is that capacitor will store the energy in its electric field, and in case of inductor we saw that it was storing the energy in its magnetic field. Alright, now the figure shows a parallel plate capacitor, this figure here, which is connected across a voltage source which is V, and it is the charge stores across the plates of a capacitor is proportional to the voltage applied. So the Q charge that is that you can see, which is accumulating on both the plates of the capacitor, the amount of this charge is basically proportional to how much voltage we are applying across this capacitor. And if you remove this proportionality, then the proportionality constant will be this capacitance. So Q is equals to CV. Alright, now coming to some important points related to capacitor. The first thing is that I've already told you that this capacitor is storing the energy in its electric field whenever the voltage across capacitor gradually increases with a certain current direction through it. Now look at the first diagram here. You can see the polarity of the supply, and you can also see the polarity that across the capacitor, and you can also see the current direction, which is IC. So the current direction right now is from the source to the capacitor. In this scenario, this capacitor is actually storing the energy in its electric field, and the current here basically is IC. So whenever we are charging a capacitor, this is the scenario we can see. And now what will happen when this capacitor is fully charged? To release the stored energy in the capacitor, it will reverse its current direction and gradually the voltage will drop across it. So as you know, in the previous video, if you have seen, in case of inductor, what it was doing, in order to discharge itself, it was basically reversing the polarity across it, but the current direction was same in both the cases, and the current was actually decreasing gradually. But the reverse case is here in case of capacitor. In case of capacitor, when it is fully charged and now it wants to discharge, what it will do, it will reverse the current direction, which you can see in the second diagram. You can see here the direction of this current is changed, and you can see that the polarity across the capacitor has not changed. So that is the thing about this capacitor. To discharge, it reverses the current direction, keeping the voltage polarity same, and this voltage will now gradually decrease across the capacitor and it will totally discharge through the supply. Okay, so that's why we see that the sudden change of the voltage is not possible across a capacitor. So whenever we have a pure capacitor, we say that we cannot suddenly change the value of voltage across it. Why we cannot do that? That we will see in a while in this lecture. First, let us go through some very important equations related to capacitor. The first one that I have already told you, that the charge stored is always proportional to the voltage applied, and that becomes Q equals to CV. Now If I differentiate this above equation with respect to time, what will happen? This will become dq by dt, right? And dq by dt is equal to I. So this is I here. Now I'll differentiate voltage with respect to time, keeping the capacitance constant, and I will differentiate the capacitance with respect to time, keeping the voltage constant. Now this term here, dc by dt, will become 0 if I say that the capacitor here is a has a static value of capacitance. So the constant differentiation will become 0. So the I will be equal to C dV by dt. And we have also seen that Vc, the voltage across the capacitor, is equal to 1 by C 0 to t I dt. The energy stored is given by half CV square, or half Q into V, and half Q square by C. Now let us look at some basic properties of a capacitor. The power dissipation in a pure capacitor is equal to 0. So we know that the complex power S is equal to P plus JQ. This one is the active power and this one is the reactive power. So in case of a pure capacitor, this P part here will be equal to 0, and the only energy that is stored in the pure capacitor will be corresponding to this Q part, that means this imaginary part. Capacitor stores the energy in the form of electric field. We have already seen that. And for a DC source, under the steady state condition, a capacitor will act as an open circuit. Now let us see why a capacitor acts as an open circuit when it is connected across a DC source. In this figure, this capacitor is connected across this VC, which is a DC source here. Now, as it is a DC source, the voltage here is constant, and we know that IC here is equal to C dVc by dt. Now the differentiation of voltage across the capacitor will be equal to 0 because this voltage here is constant. Now as dVc by dt is 0, IC will also be equal to 0, and IC equal to 0 is giving us a hint that the current through this capacitor is 0 in this condition, and 0 current through a branch indicates that it is a open circuited path. So as the current is 0, it is indicating that it is an open circuited condition for an element, and that's why we say that capacitor always acts as an open circuit whenever it is connected across a DC source. Okay, one more thing. I told you that we cannot change the voltage suddenly across a capacitor. Why so? Because we say that we are trying to make a dV change in the voltage. That means this is the change in voltage, which is some finite value. I want some finite change in my voltage, but the dt value is 0 here. That means I do not want to give my capacitor any time for that. Okay, so I is equal to dV by dt. So this dV is some finite value and it is divided by this dt here, which is 0. So this will result in an infinite current, which is not practical. Practically infinite current is not possible. So therefore change in voltage instantly across a capacitor is also not possible. All right. Okay guys, so that's all for this lecture. From the next lecture, we will start a new section of this course, which is the Kirchhoff's current law and the Kirchhoff's voltage law. We will also see what type of sources are there in our circuit. So all of these things we'll see in the upcoming lectures. So thank you very much. I'll see you in the next one.